So we are in Unit 4. Unit 4 is a structural idealization. Structural idealization is a process in which actual geometry and the load acting on is converted into a simpler model for the purpose of analysis. That is, in order to solve a complex geometry, complex structure, we convert this complex structure into a simpler mechanical model for the purpose of analysis. So for example, when we have a wing cross section, so wings have a spars, so let's assume this is a front spar and this is a rear spar, and we have other stiffener membrane, and the wing is called as fringes. So I mention it like Z. So it's a replica of our actual wing section. This is spar and this is a stringes. Okay, so when we want to do analysis of this complex geometry, it is a tedious and difficult process. So what we do, we will convert this a model into a simpler one based on some assumption. Let's see. Okay, the same thing. So now what I do, so I make these fringes and spars into a small dots. Like this, I make two small dots. So we have a connections here. Okay, 1, 2, 3, and we have connections. So this is a idealized wing section for the analysis. So we have converted these stringes and spar into small dots, which is called as a booms. So how we change these stringes and spars into small dots, and what this booms indicates? So booms indicate a concentrated area of stringes and spars. So these booms indicated the area of stringes and spars. So this is just booms is a area. So what will be the unit? It will be in meter square, centimeter square, millimeter square. So what are the other assumption we made? The other assumption, these stringes and spars will carry only direct stress, and skin will only carry shear stress. Although this skin carries a direct stress, we are not considering in our assumption. So we assume that skin carries a shear stress and stringes and spars will carry a direct stress. So, and also the booms will indicate indicates the concentrated area of the stringes and spars. So here these both the actual and idealized wing structure have to behave in a similar manner under any loading condition. For example, when I apply a load of 1000 Newton, for example, when I apply a load of 1000 Newton in actual and idealized condition, so at some point, so I identify stress. At some point, I identify stress. It has to give the same value. For example, if the idealized one gives a 50 Newton per meter square, so the actual one also has to give 50 Newton per meter square or with a small variation. So it has to behave in the same or a similar manner. Okay. So now these are the assumptions we made. So now we will go and check what these booms are related to, what is the empirical relation between the actual and the idealized model of these booms. So for that, in order to describe that one, I will take a panel. I will take a small panel. Okay, so there the load, so the stress is acting sigma 1 and it is the uniformly distributed, uniformly varying load. Okay, it will be sigma 2. So okay, the stress is varying like this. So I will redraw the stress. Okay, the stress is varying like this. There are two sections. We have a rectangle and a triangle, sigma 1. So the thickness will be TD equal to T, and the length of the section will be B. So now this is the actual section. Now we will convert this into idealized one. So for our assumption, we have made these booms will carry a direct stress and this panel will carry, the skin will carry a shear stress. We have uniformly distributed stress. So what we do, so we convert into two booms. Okay, two booms. I mentioned as the B1 and B2. Okay, B1 carries sigma 2. Sorry, B1 carries a sigma 1. And B2 carries a sigma 2. So it will running along the section. Okay, now the skin will carries a shear. So the thickness is T and it will be equal to 0, and we assume, and the length is B. Okay, so in our assumption we have made both this actual and idealized model as to behave in the similar manner. So when I take a moment at this point, this region, when I take a moment at this region of the actual and moment at this region of the idealized one has to be same. Okay, according to our assumption, so these both are actual and idealized model has to behave in the same manner. So in that case, if I take a moment at these regions, it has to be same. So I mentioned this region, moment on actual has to be same with the moment on a idealized region. Okay, so in this region, so we have a uniformly distributed load, and it will be varying like a triangle and a rectangle. So first we consider this rectangular region. First we consider this rectangular region. So stress here is sigma 1 and sigma 2. It is uniformly varying. So for rectangular region we consider a sigma 2, and the area acting on the region will be this one. So it will be T into B. T into B. Okay, so we know moment equal to force into perpendicular distance, right? So here the force is sigma into A. So what is our stress here is sigma 1, and the area is a T into B, right? So this is our force. The perpendicular distance is like the force concentrated on this rectangle. It will be at a distance B by 2. So from here to here, so it will be into B by 2. This is the moment for the rectangle. So now the moment for the triangle. So triangle this region. Okay, so here also the same manner, but here it is a little bit tricky. So here we have both the influence of sigma 2 and sigma 1. For here the force equal to sigma into A, but this sigma, so we will take the average stress first, sigma 1 plus sigma 2 divided by 2. So we will take the average stress of this region, and we minus this sigma 2 value, sigma 2. So now we will get sigma 1 minus sigma 2 by 2. So this is our stress, and the area will be the same region here, this one. It will be T into B, right? T into B, and we have to determine the force concentrated on this rectangle, which will be at the centroid. The centroid for the rectangular triangle will be 2 by 3 into B. So this will be the moment for the triangle. So on the left hand side I can write sigma 1, so this one, sigma 1 T B square by 2, so plus sigma 1 minus sigma 2 divided by 2 into 2 by 3 T B square equal to, now the right hand side here, so we are taking, so force into perpendicular distance, okay. So what is our force? Sigma 1 here, this one, sigma 1 into the area is B1 into the perpendicular distance is B. So it's sigma 1 B into B, B1 into B. So it will be sigma 1 B1 into B. So now we do a simple arithmetic simplification. So we have a B common, okay, and we keep B1 at some side, and we will move the other parameter sigma 1 to the other side, and we simplify. We will get B1 equal to TD into B divided by 6 into sigma 2 by sigma 1 plus 2. So this is the final empirical relation we get for the booms. Okay, that's it.